Okay, so let me remind you what was going on in the lecture before we had our revision session. So we looked at open balls and closed balls, and I'd given you the notation for that. I'd reminded you about nested intervals in the real line, and of course there's a corresponding version in finite dimensional space. But we're moving into more general complete metric spaces now. So our next task is to prove this nested balls lemma about nested decreasing closed balls in complete metric spaces. So here, and I've given you all these warnings about this, you've got your nested decreasing sequence of closed balls and the radii tending to 0, and you assume you're in a complete metric space, then there's going to be exactly one point in the intersection. Once we've done that, we'll be able to prove the Baire category theorem, which we discussed a bit last time. So let's prove lemma 1.4. So you've got this complete metric space, you've got a sequence in there, you've got these nested decreasing sequence of closed balls centered on x z radius Rn, and the radii tending to 0. So let's have a quick sketch of the setup then. We're starting from n equals 1. So you've got some big, perhaps a big closed ball centered on x1 radius R1. The sketch is not a proof, of course, but just to remind you what's going on. Then somewhere in there, and you don't know exactly whereabouts in here, there's another closed ball. So this is the closed ball centered on x1 radius R1. Somewhere in here, you've got a closed ball centered on x2 radius R2. Maybe it's here. And so on. You don't know where they go. But that's a picture to bear in mind. And now we're going to prove this result about the nested balls. So we're going to prove lemma 1.4. Now, because the radii tend to 0, it's rather easy to prove there can't be more than one point in the intersection. So because Rn tends to 0 as n tends to infinity, it's easy to see, you can check the details of that for yourself, that there cannot be more than one point. In the intersection of all of these balls. If I leave out any bars over the top, that's a mistake. They should all have bars over the top, because this is a result about closed balls. I'll just see whether I've got the bars in these ones. Yes, I have. Good. Right. So there can't be more than one. If you had 2 points in there, say, they're different, they'll be a positive distance apart, and that will quite quickly violate the fact that they're both supposed to be in the same very small ball, so that's not possible. But I'll let you fill in the details of that. So our main task then is to show there's at least one point, and therefore exactly one point. So we have to prove it's non-empty. So it remains to prove that that intersection is non-empty. Okay, so we'll prove it's not empty, and we'll do that by showing that the sequence xn itself is a Cauchy sequence and that the limit is in the intersection. So it's the same xn, the sequence of centres, will show the Cauchy sequence and that the limit of this sequence is in the intersection. Okay, sorry. Anyone need more time on the slide? Did anyone need more time to write that down? You okay? Good. Right, so let's start by showing it's Cauchy. So this is stage one, if you like. Let epsilon greater than naught. Now the point is these closed balls are nested, so whenever you get to any particular stage, all of the remaining points are in that closed ball. And when you move a bit further on, they're in the next closed ball. And remember, the radii are tending to 0. So to be a Cauchy sequence, we want to make sure that the terms are strictly within epsilon of each other from some point onwards. So I'm going to need an epsilon over 2. Actually, there are two different ways to do this bit. I'll use an epsilon over 2 method. So since Rn tends to 0 as n tends to infinity, we can just choose a capital N in the natural numbers so that I'll take it just that R sub capital N is more than epsilon over 2. Now, since the closed balls are nested decreasing, for all m and n greater than capital N, and of course we're talking natural numbers here, we have xm is in the ball centered on xm, radius rm, that closed one, that's contained in the closed ball centered on x capital N, radius r capital N, and similarly xn is also in there, in its own one, so the closed ball centered on xn, radius r capital N, r little n, which is also a subset of the same big closed ball centered on x capital N, Rn. Okay, I say it's big, but it's got radius less than epsilon over 2, so it's probably small, really. So the distance from xm to x capital N and the distance from xn to x capital N are both less than epsilon over 2. Well, they're both within r capital N at that point, and r capital N was less than epsilon over 2. Thus, the distance from xm to xn, which is what we're really interested in, that's less than or equal to the distance from xm to x capital N plus the distance from x capital N to x little n, then it's capital N there. And so that's smaller than epsilon over 2 plus epsilon over 2 equals epsilon. So we proved the sequence is Cauchy. From some point onwards, all of the remaining terms are within epsilon of each other. Remember, it's not enough to check that successive terms are close together. That's not enough. It has to be that once you go far enough along the sequence, all of the remaining terms are close to each other. Being close to just the next term in the sequence is not good enough as well. I'll leave that as an exercise. You can find a sequence that isn't Cauchy, but which does have the terms getting very, very close together, as long if you were only looking at successive terms. Right, okay, so xn is Cauchy in X. Since X is complete, or since XD is complete, okay, we'll say it's in XD just to be more accurate. Since XD is complete, Xn converges let's say Xn tends to X and then tends to infinity, X being a point in X, and we claim that X is in the intersection of them all. We claim that X is in the intersection of everything. Of all of these closed balls. Right. Well, why is that? Well, the reason for that is, of course, because, again, they're nested decreasing closed balls, and after a while, the tail of this sequence is inside a given closed ball. So let n be a natural number, then for all m greater or equal to all m greater or equal to little n, we have, just as before, as above, that xm is in the relevant closed ball. So xm is in the ball, the closed ball set on xn, radius Rn. But now if we keep n fixed and let little m tend to infinity, for the moment, letting m tend to infinity, we see that limit as m tends to infinity xm is also in the closed ball because that's a closed set. That limit is, of course, x, so x is in that closed ball. But that was true for all natural numbers m, so we finished. So x is in the intersection of all the closed balls, which is what we wanted. Any questions about that proof with nested closed balls? People are happy with Cauchy sequences? The fact that they converge in complete metric spaces and so on? Okay, good. So that's the key lemma. With that lemma, we can prove the Baire category theorem easily enough. So now we're going to prove theorem 1.5, which is a Baire category theorem, so I'll just repeat the statement here to save me going back to the other slide. So that's so here's the statement. XD be a complete metric space, and let UN be dense open subsets then the intersection from n equals 1 to infinity of UN is also dense. In X. Okay, we need to choose our favourite definition of dense to decide how we're going to prove this one. Who can remind me of a definition of dense? Anyone want to tell me a definition of dense for metric spaces? There are actually several different equivalent ones. In fact, we're better off with the topological definition here, but let's just... Okay, so before we do the proof, let's recall some stuff about... Recall the definitions of dense. A set A contained in X is dense in X.
Can I try to define it?
Okay?
If the open set in X,
Yes.
the intersection between that open set and A is not empty.
Okay, so that is nearly perfect. Let's write down that, and then we'll see if there's one missing word. It is a very important missing word, though. So it's dense in X if for every open set, what should we call our open set? We've got U's. Let's have V contained in X. We have A intersection V is non-empty. Okay, which is almost perfect, but there's one word missing, without which it's actually impossible for a set to satisfy this. That's the one. But, having said that, I often see people miss that word out. So it's very common to miss this word out, but unfortunately, without saying non-empty, it's impossible for any set to satisfy that condition, because the empty set is open. So since the empty set is open, of course, you can only arrange to meet non-empty open sets. And so that's the key. So that is the key. And that's the one we're going to work with. But the other equivalent definitions are... That's right. So equivalently... that's if A closure equals X. Or you can have sequential denseness. Since it's a metric space, it's equivalent to the following: for every X in X, there exists a sequence AN contained in A, such that AN tends to X as n tends to infinity. And that's quite a useful notion of density using, or denseness maybe, using sequences. Yes. Oh, yes?
The closure of pi is equal to x. So the interior of pi is the same as the interior of x.
No, because think of the rational numbers in the reals. Rational numbers are dense, but the rational numbers have got empty interior. But the closure of the rational numbers gives you the whole real numbers. So, interior, so you shouldn't look at interior. Denseness doesn't usually help you with interior, because you can have something like the rationals with no interior at all, but still being dense in the real line.
Because the interior of the closure is not equal.
That's right. The interior of the closure does not necessarily bring you back to where you started, even for open sets. The rational numbers are not open, of course. But even for open sets, the interior of the closure doesn't necessarily bring you back to where you started. Right, so, well, yet again, we've lost the statement. So I'm going to assume that you've got the statement in front of you. And I've got the statement in front of me. So we've got a sequence. So we've got the proof of 1.5 coming up. So proof of the Baire category theorem. By the way, notice that I didn't assume that X was non-empty. X could be empty. If X is empty, then everything is completely boring mentioned here, because the open sets have to be the empty set. The empty set is dense in the empty set, but it's not very exciting, and so on. The empty set is a rather boring exceptional case. So we've got XD, I'll remind you again, is a complete metric space. And UN are dense open subsets. And we have to prove that the intersection from n equals 1 to infinity of UN is dense in X. That's our task. Okay, so let's suppose we've got a non-empty open subset of X, and we have to show that this set meets it. So suppose that V is a non-empty open subset let's say that again, a non-empty open subset of X, and our task is to show that the intersection of all those UNs intersected with V is non-empty. So we show that V intersection from n equals 1 to infinity of UN is non-empty. How do we do this? We do this using the closed balls lemma, and what we do is we find a nested decreasing sequence of closed balls, each one of which is contained in a bit more of this. So we do this by constructing inductively a nested decreasing sequence of closed balls centered on xn radius Rn with Rn tending to 0 and such that for all natural numbers n the ball xn closed ball centered on xn radius Rn will be contained in, actually it's going to be contained in V intersection, the intersection of the first few from k equals 1 up to n of uk So let's see how you do that. Right. Well, once we've done that, the rest will be easy because we'll apply the lemma. And the point you get at the end will be in V intersection the whole thing. Well, how do we start? Well, we start, since U1 is dense, and V is non-empty and open, we get U1 intersection V is non-empty. It's also open because U1 and V are open. So you start, you've got a non-empty open set, and we just choose any x1 in there. Now, U1 intersection V is open, so then we can choose an R1 greater than 0 so that the ball centred on x1 radius R1 is contained in there. But I want to make a couple of extra conditions on that. I want to make sure that R1 is at most a half, because if you find one R1 that works, you can always choose a smaller one. So we'll make R1 less than a half. And I'll make sure the closed ball is contained in there, which again you can do. If you get the open ball contained there, then you can go to a slightly smaller one to make sure that the closed ball is contained in there. With R1 smaller than half, and the closed ball centred on x1, radius R1, should be contained in U1 intersection V. So let's have a diagram of that. So what am I up to? I've got U1, I've got V. Let's have some pictures of that. Here's U1. Here's V. I chose my x1 in there somewhere. And then it's in an open set, so I can find a small radius. If I take a small enough radius, then the open ball will be inside that intersection. If I take an even smaller radius, the closed ball will be inside the intersection. And if I take an even smaller radius than that, I'd have made sure that R1 is less than a half. So this is no real problem. Oh, actually, no, I'm sorry. What am I doing? I want the closed ball to be in there. So your closed ball, centred on x1, radius R1, miswrote that. Closed ball, centred on x1, radius R1 is contained in that intersection. Okay, so that's got us started. Now the question is, how do we choose the ball, the closed ball centred on xn plus 1, radius Rn plus 1, once we've chosen xn Rn? So having chosen xk and rk for 1 small equal to k small equal to n, we'll choose xn plus 1 and Rn plus 1 as follows. And they'll have been nested so far. And I want to make sure they stay nested. Actually, I'm going to make sure each new closed ball is contained in the open ball from before. Since the open ball, centered on xn, radius Rn, is non-empty and open, you can intersect it with the n plus 1th dense open set. So that's because un plus 1 is dense and open. So you choose any xn plus 1 in that set, and choose Rn plus 1 greater than 0 with, and let's make sure it's at most 1 over 2 to the n plus 1. It doesn't really matter how tough you are. As long as you've got something tending to 0, that's the main thing. With Rn plus 1 at most 1 over 2 to the n plus 1. And so that similar to before, the ball centered on xn plus 1, radius Rn plus 1, closed ball is to be contained in that intersection. Ball xn Rn, the open ball intersected with un plus 1. So that's a similar diagram to before, very similar diagram to before. So this time it looks a bit like this. Here's your ball, open ball, centered on xn, radius Rn. And here's, I won't bother putting xn and Rn in. Here's un plus 1. And now, again, you pick an xn in here, an xn plus 1 in here, and you choose a nice small radius so that the closed ball centered on xn plus 1, radius Rn plus 1 is in there. Does everyone now see how this inductive construction is going? You now carry on with this, and you can see that you can carry this on, and this gives you a sequence. Now, you're using the axiom of choice, unfortunately, but sequential choice, which is not as bad as the usual thing. So once you've chosen a few, you now see how to choose the next one. And this gives you a sequence of xn's and rn's satisfying the conditions of the lemma. So we get two things. We now see that the closed ball centered on xn, rn satisfy the conditions of the lemma, also the ball centered on xn, Rn is contained in the intersection of V with un for all n, but they're also nested decreasing. So in fact, since they're nested decreasing, the ball Z on X Z Rn is actually contained in the intersection of the first few. You can actually pick this out. From what I'm about to say anyway, you can pick out everything you need, but you may want to observe that actually it's contained in the intersection of the first few. Because each of these balls is contained in its own UN, and they're nested decreasing, so each one is contained in all the previous ones as well. Now we apply the lemma. And the uniqueness doesn't matter so much. So by lemma 1.4, the intersection from n equals 1 to infinity of B of these closed balls is non-empty. But if you intersect the ball, it's contained in V intersection, the intersection of all the open sets. Doesn't matter whether you use K or N. So the result follows. We've proven this thing is non-empty, this intersection. That's true for every non-empty open set V. And so the intersection from K equals 1 to infinity of UK is dense in X. Any questions on that proof? I drew lots of diagrams. Any questions on any of the bits? I did say before that although the intersection is dense, the intersection doesn't necessarily have to be open. That's in spite of the fact that if you intersect finitely many open sets, you will get an open set. But if you intersect infinitely many open sets, you might not anymore. So I have mentioned already in lectures an example of something which could happen here where the resulting set isn't open anymore. Can anyone remember any of the things I've mentioned in lectures that might give you an example where everything else that's going on here does happen, but where the resulting set isn't open anymore? Can anyone think of one? Okay, so you can use the irrationals, and that's right. You can get the irrationals, which are clearly not an open subset of the real line, but you can get it as a countable intersection of dense open subsets of the real line. So note that R take away Q is a dense subset of R, which is not open, but you can get to R take away Q as an example of something you can do in the Baire category theorem. But R take away Q is an intersection of a sequence, countably many, of dense open subsets of R. Okay, so that's a Baire category theorem, but we haven't really seen the full power of what it's used for yet, apart from the fact I've told you can do most of my challenging questions using it, which is already a good thing. So let's have a quick look and see, again, some of the comments we had before. So I mentioned this before. We did this topologically. Because we used a topological definition of dense, we didn't use a metric definition of dense. That all works as a topological space result for complete metrizable topological spaces. And I told you what a G delta set was, that it's a countable intersection of open sets. So we get this corollary that I mentioned before, that you can do the same thing in more generality. You just say you've got a complete metrizable space and a sequence of dense G delta sets, then the intersection will still be dense, but you get the nice extra feature that it's a dense G delta set. So you've got a bit more information there. And now, this corollary is a very nice one to know, that if you've got a complete metric space with countably infinitely many points in it, then it has to have infinitely many isolated points. There's going to be a nice question on a question sheet where I'm going to give you a false proof that all of the points are isolated on one of the question sheets, and then you have to find the mistake. Because that's not true. But you can show that if you've got a countably infinite metric space, which is a complete metric space, then it has to have infinitely many isolated points. And from that, you get, since the rational numbers have got no isolated points at all, then you know it's not complete metrizable. And that answers one of the exercises from earlier. It's not the only way to do it, but it's quite nice. The fact that the rational numbers have no isolated points, but that it's countable, stops it from being complete metrizable. Which means, because of something else I said, it couldn't be a G delta set, which you can also prove directly from Baire category theorem. Of course, if you have a finite metric space, then all of its points have to be isolated. And if you have an empty metric space, then all of its points are isolated, but it's not very interesting because they haven't got any. But if you want to insist you've got infinitely many isolated points, then you'd need an infinite space in the first place. So that's why you do this one. But the main point about corollary 1.7, the main point about corollary 1.7 is that you can show there's at least one isolated point, in which case you could apply that to some of the other situations as well. Once you've shown there's at least one isolated point, the rest comes from an easy induction. So I'll just finish off by saying this is easy once you show X has at least one isolated point. Because once you've done that, you take that point away and look at the rest of the set, and it's still complete metrizable, and then it still has to have an isolated point, and so on. And that way you pull out a sequence of isolated points. And you have to think about it a little bit in view of the false proof that I'm going to give you on one of the question sheets, but it works fine. I'll say a little bit more about that next time. Okay, I think we should stop there today.